Hey, welcome back to your favorite pre-cal class. This is section 2.4, Library of Functions and Piecewise Defined Functions. We're going to remind you about the classic parent functions, and then we'll take a look at how those can help you in graphing piecewise defined functions. So let's start off with the square root function. So f of x equals the square root of x. If we were graphing this thing and we're plotting some points, let's throw 0 in. So if you're taking the square root of 0, of course it's 0. 1 would be another good one. Square root of 1 is 1. 4 would be another good one because I know the square root of 4 is 2. I know 9 is a good x value to pick because I know the square root of 9 is 3. Soon enough we graph this thing 0, 0, 1, 1, 4, 2, 9, 9, 3, and your square root function looks kind of like this. Alright, let's talk about some of the properties of it. Notice it is increasing throughout its domain. Notice that the domain starts with an x value of 0 and keeps going to the right, or if you want to write it in set notation, that would be x such that x is greater than or equal to 0. Your range, lowest y value is 0, and it keeps going up, so you got 0 to positive infinity, and then you would have y such that y is greater than or equal to 0. Okay, so you've got all these properties involved with the square root function. There's a better look at that. Now let's do the cube root function, so the third root of x. So if you're picking some points, throwing 0, the third root of 0 is 0, third root of 1 is 1. 8 is another good one because we know the third root of 8, just to remind you, you're looking for 3 of a kind. 2 times 2 times 2 is 8. So you got, as soon as you got 3 of a kind, you have your answer. So third root of 8 is 2, right? Because the third root of x equals y just means that x equals y cubed. That's what that means. So that's why you're looking for 3 of a kind on that. You can take the third root of negative 1, that's negative 1. Third root of negative 8 is negative 2. And then you graph this thing. So you got 0, 0, 0, 0. You got 1, 1. 8, 2, negative 1, negative 1, negative 8. Negative 2. Anyways, you keep graphing this. That's kind of what this third root looks like. Notice that your domain is all real numbers here, right? Right to left, all reals. Your range is all reals. Notice it's increasing throughout it. Okay. Your x-intercept and your y-intercept is right there at 0, 0. So there's your third root function. That's a little bit better look at that. Okay. It doesn't go out as far as I did before, too. Alright, so that brings us to, there's your properties on that. Oh, I did forget to talk about, is this even or odd? Well, this is odd. Notice you got the point 8, 2 here. You got the point negative 8, negative 2 on that. So any x, y, you've got negative x, negative y. So this third root function is an odd function, whereas a square root function is neither even nor odd. Neither even nor odd. Okay, so that brings us to the absolute value functions. Y equals the absolute value of x. If we were graphing some points there, absolute value 0, 0, absolute value 1, 1, absolute value 2, 2, absolute value of negative 1 is 1, absolute value of negative 2 is 2, and so on. And you graph this thing, and once you start plotting these points, 0, 0, 1, 1, 2, 2, you graph it that way, negative 1, 1, negative 2, 2, graph it this way, you see that V. Alright, so this is what the absolute value function looks like. Your domain, notice, goes clear to the left, clear to the right. This domain's all real numbers. The domain is all real numbers. The range, if you notice, there's your lowest y value. So it goes from 0 up. So your range is going to be from 0 up, or y is greater than or equal to 0. It's an even function. Notice you got the point 2, 2. You've also got negative 2, 2. This thing's even. It is not odd. It is even. So there's your absolute value function. Here's a little bit better look at that absolute value function. Okay, and some properties about that. Alright, the constant function. So constant function, that would be like y equals any old constant. Let's pick 4, for instance. If you can't remember what the constant function looks like, just use the equation that you got there. Y equals 4, so you know y is always 4. Doesn't matter what your x is that you pick here. There's no x to plug in anyways. So you got y equals 4. You graph that. Negative 2, 4, negative 1, 4, 0, 4, 1, 4, 2, 4. You graph that and you're like, oh, that's right. That's a horizontal line, y equals 4. And you notice this is even. It's reflective about the y-axis. You got that point 2,4. You've also got that point negative 2,4. So this is an even function. Your domain is all reals. Domain is all reals, x such that x is an element of the reals. Your range, on the other hand, is only a y value of 4. So y such that y equals 4. Or if you're doing that in interval notation, you would just say 4. You put that thing in brackets. Okay, so that's your constant function. So any constant function is horizontal line. That brings us to the identity function. So here's your classic line. Y equals x, right? You can graph that thing. If you notice, this thing is symmetric with respect to the origin. You have the point 3, 3. You got the point negative 3, 3. Domain's all reals. Range is all reals. Okay, so this is the classic identity function. So every line is some sort of manipulation of this identity function. Y equals x. Well, here's your square function. We've done the quadratics before, right? This thing's even. You see the 2, 4, negative 2, 4. Domain's all reals. Range is from 0 up, right? The range is from 0 up, so this is your square function. Every quadratic is a manipulation of that graph there. Here's your cube function. So like you would have the point 1 cubed is 1, 2 cubed, you'd have the point 2 comma 8 up here somewhere, 2 comma 8, you'd have negative 2, negative 2 cubes, negative 8, so you got the point negative 2, negative 8 down here. This thing is odd. Any x, y, you'll have negative x, negative y. Domain all reals, range all reals on that. The reciprocal function, that's supposed to show a little line. 1 divided by x. Okay, so if you're plotting points, you throw like 1 in. 1 over 1 is 1. Throw 2 in. 1 divided by 2 is 1/2. Throw 3 in. 1 divided by 3, 1/3. Throw 4 in. You know, 1 over 4, and so on. And you notice if you're plotting those points, 2 comma half, 3 comma third, 4 comma fourth, what's happening is you go to the right, this thing is going further and further, closer and closer to 0 is what this is doing. Okay. Then you could plug in a half, you know, and if you're plugging in 1 over x, x is a half in this case, keep change flip on that, so you end up with 2, right? Y equals 2, so you got 1/2 comma 2, you notice it right there. You can plug in 1/3 and so on, but you're going to notice that this graph just keeps climbing up like that. Okay. So you'll never touch, notice x can never be 0. You cannot divide by 0. So your domain is going to be anything except 0. X such that x is an element of the reals except for 0. Okay. And your range will also not include 0. You'll never touch the y value 0. This gets closer and closer and closer. Notice it goes out, but you'll never touch 0 on that. So your y such that y is any real number it'll hit, but not 0. This is an odd function. Notice the point 2 comma half right here, and you got negative 2, negative a half right there, right? So any x, y, you'll have negative x, negative y. This thing is a reflective about the origin. Okay, that brings us to piecewise defined function. So if you've got this function, negative 2x plus 1, and you've got, piecewise defined function, first of all, is a function defined by two or more equations. Okay, so you've got this negative 2x plus 1, and it's only defined between less than 1, x is less than 1, but greater than or equal to 3. So what I like to do when I graph these things is I'll take this negative 2x plus 1. You know what? Let me insert. Okay. So I'm going to graph this part of it first, negative 2x plus 1, and I'm going to do it with a table of values. So I'm going to use the fact that it is only this line, negative 2x plus 1, when I'm less than 1, and I'm greater than or equal to negative 3. Okay, so 1, 0, negative 1, negative 2, I'm going to go down to negative 3. Now notice, I'm strictly less than 1. So this has got to be open. I cannot include the 1. But I'm greater than or equal to negative 3. So this will be closed. I will include that negative 3 right there. And then I'm going to plug those in one by one. Let me plug the 1 in for the x. So negative 2 times 1 plus 1. I got negative 2 plus 1 is negative 1. Let me throw 0 in now. 0 plus 1 is 1. Let me throw in the negative 1. Now I got negative 2 times negative 1, 2. 2 plus 1, 3. Throw in the negative 2 and I get 5. Throw in the negative 3 and you get 7. And you can start graphing what this looks like. Oops. Let me erase a little bit here. I didn't leave myself enough room with this. Oops. Alright, so let's plot this. So we've got 1, negative 1. And this is open. This is open. I have 0, 1. I include that. I have negative 1, 3. I include that. Negative 2, 5. Include that. And finally, negative 3. Negative 2, 5 is right there. Come on. 2, 5. And then negative 3, 7. I also have on my graph negative 3, 7. I got to erase some of this. Negative 3, 7. Okay, right up to there. And that negative 3, 7, oh, come on, is included. So it's filled in. Because it was greater than or equal to. Okay, so there's the line portion. There's the negative 2x plus 1. When x is less than 1, greater than or equal to negative 3. Now, y equals 2. See this y equals 2 part? F of x equals 2. Whenever x is 1. So when x is 1, y is 2. And you just got this point. That's the only time. You got this point 1 comma 2 right there. Okay, so there's the point 1 comma 2. Let's go to the next one. Now we've got y equals x squared when x is greater than 1. So y equals x squared whenever x is greater than 1. So I'm going to start with 1. I do not include it because it's greater than 1. So I got to leave this as an open hole, denoting that I'm not including it at that point. But then I'm going to pick x values bigger than 1. So 2, 3, 4, and so on. Now I'm going to plug them into the equation, y equals x squared, because it's y equals x squared when x is greater than 1. So 1 squared is 1, 2 squared 4, 3 squared 9, 4 squared 16, and I could go on with that. So at the point 1, 1, notice it's open. At 1, 1, this has got to be open. It's open. And then I have 2, 4 included in this, 3, 9, and so on. And this is going to look like, this is kind of supposed to be a quadratic in shape here. But it looks like y equals x squared, right? So it's going to have a little curvature to this thing. I just didn't draw it too well with my points. But I'm not including that point right there. That's open. Okay, so this is a piecewise defined function. I've got this negative 2x plus 1 portion whenever x is less than 1, greater than or equal to negative 3. So there's this right there. All right. Then I've got y equals 2 whenever x is 1, and that's just that little dot right there. And finally, I've got the quadratic portion whenever x is greater than 1. So here's a little better look at that. Okay, and you can answer any questions that they might ask you, such that, what is f of negative 2? And you say, well, f of negative 2, here it is. What's f of negative 2? And you say, it's 5. All right? And so on. Well, thanks for listening, you guys. We'll see you guys in class.